Well, I could get started by saying hello, welcome to CppCon 19. My name is John Lakos. I work at Bloomberg. And today we're going to talk about something that's really near and dear to my heart. And it is a value proposition on the notion of having an allocator-aware software infrastructure. And it's my hope that after you see this talk, you'll want to go see Alistair Meredith and Pablo Halpern on Wednesday. It's the second talk in the afternoon, which is all about getting allocators out of our way. So this is the value proposition. It's a balance, and they're going to show us, they're going to tip the scale all the way over, knock it over, gone. We'll see that. So I'm going to get started. This is my talk. I just went to Norway while I was finishing this book that I've been working on for 20 years. I can now say that it's done, officially. It will be out in December of this year. It's been on Amazon since, I think, 2014 or 15. It was originally due in 2001. I'm a little late, but okay. So I'm going to get started here. This talk is something that I've been doing most of the year. I presented at ACCU and also CppCon, C++ now. This is CppCon, and I'll probably present again at Meeting C++. Hopefully this will be rather smooth. This is the copyright notice. I have to put it up, but you don't really need to read it. This is the abstract, but since you're already here, you really don't need to read it. The purpose of this talk is local allocators provide performance, and I think we all know that there is that. On the other hand, there are real-world costs. And so this talk is going to be more of an economics talk than it is going to be a purely technical talk, but it's going to motivate the reason for why we really do want to have allocators. There are a lot of important collateral benefits in allocator-aware software that you don't get from rolling your own. So it's not just that you get the performance, you also get other things. There are still some concerns that are out there, and at the end of this talk, after I tell you I'm done telling you all the good stuff, there are some concerns that we'll talk about briefly. And then, of course, after the talk is done, anybody who wants to come up and talk more about it, I will stay forever till that's done. What we'll do today, so we're going to present some allocator-aware software styles very briefly. If you don't know them, don't worry about them. They're all more or less the same. We're going to separate real from imagined costs, discuss some of these important collateral benefits, address some common concerns. The concerns are in quotes. That's really fun. And then I'm going to say, you know what? All things considered, I think it's a pretty good thing to have allocator-aware software today. And so I'm going to make this detailed analogy. And then I'm going to say, but what if? So that's the talk. With that in mind, this is the introduction. And moving right along, dynamic memory allocation is important, right? New and delete. Sometimes we can get by with that. Sometimes we can't. Custom allocation gives us advantages. And sometimes it's absolutely necessary. We just can't do our jobs without that. Implementing this custom allocation is always costly. You can't get away from it. If you're going to do custom allocation, it is going to cost you. And that's what motivated our having an allocator-aware software infrastructure, so at least the application developers would have a huge head start and wouldn't have to spend the time rolling their own. And again, go to Alistair and Pablo's talk on Wednesday and see the magic. So, two approaches to custom memory allocation. One is roll your own, has the best possible performance, has huge development cost. The other one is to have an allocator-aware software infrastructure in which it's mostly pluggable, gives you almost as good performance, gives it to the application developer at phenomenally lower cost, no question about that, and some collateral benefits. So that's good. The best part of this talk clearly is my airline analogy. So I hope that this will hit home. It was a hard sell at first, but I've refined it. I hope it works. So everybody knows that first class, right? Best possible. Economy, cheapest possible. That's what things started out being. And this is from the client perspective, right? So we have this airplane. It has a little space for first class. It has this big cabin for economy. And then if you could imagine, if we lined up all of the use of software that we have, like if you imagine physical entities, I call them components, we lined them up in order from the component that could care the least about allocators. Imagine whatever criteria you use to the component that couldn't live without having the absolute best custom memory allocation on that scale. So you imagine ordering them. There's going to be a utility curve that goes from essentially 0 to something close to infinity, right? Can you imagine? It's going to go very high. Somewhere, I think without too much argument, we could say that, well, somewhere there's a point where someone who needs it would write their own. Does that seem fair? Somewhere there's that partition where we say on this side of that, these need custom memory allocation. They need it. And on the other side, they don't. We'll call that alpha, okay? Now, I'm going to add a new axis, cost. It's on the same graph because we have this same utility curve here. We're going to superimpose two curves, which is going to confuse everybody, but I'm still going to do it. And so these are different axes. One of them is utility, which is smiley face in green, and one of them is cost, which is frowny face in red, okay? And so here, it costs nothing up to this point because we're not going to do anything, right? If we don't have any alternative, we're going to go economy until the point that we have to go first class, in which case we're going to spend all the money it takes to roll our own, and then we're going to go first class. So that's what the cost curve looks like before we introduce anything else. Does that make sense? Right? If you can go economy, you will. But if you can't, if you must go first class for whatever reason, then you must. And that point is alpha. And that's how people are divided. Okay, so there's this enormous cost for all of those high performance, low latency, critical applications. We have to spend that money. All right. So this is the value that we get, though, under that curve. If you look at that green, we are getting all of that good value for our money. It's a lot of money, but we're getting value for it. It wouldn't make sense to write all of our software that way. That would be nuts. But at some point, it's worth it. Okay? Now, imagine we have business class and premium economy. What is business class? It's a cheaper first class, still gives you tremendously good value, but at a lower price, right? And then if you look at premium economy, it's the other side. It's saying for people who really don't need it, but they'd like it, if you spend a little bit more, we'll give you a little more legroom, a free drink, maybe a sandwich. You know, it's a little bit more money, a lot better. Well, if you imagine that analogy, what it does is it creates another tier of price discrimination. And so let's say that premium economy starts at alpha minus. With me so far? And let's say that business class ends at alpha plus. Okay? So we have the middle section, upper class, there. Okay? What is that? Well, that's not economy, and it's not first class. But it's the best of both worlds, in some sense, rolled together. All right. So, premium economy, and this is business class. Here's our cost function. And for people who just don't care, they spend nothing. We're talking about application developers. This is from the application developer's perspective. Then, for people who care a little bit, but wouldn't write their own, because premium economy is so darn cheap, yeah, for another $29, yeah, sure. But then there are these people that would have rolled their own, and they spend the same $29, and they get the same benefits of business class because we're not distinguishing between premium economy and business class in this model. So it's the same price for premium economy and business class. You pay premium economy prices, you get business class stuff. So that's a low cost. Then, of course, there's going to be the people that I've got infinite money, I don't care, I'm going first class. Bless you. Okay. All right. So those people still get their value, right? But the other people still get their value too. So that green curve is just as good as it was before. But now look, bonus, there's a whole bunch of people that wouldn't have rolled their own that also benefit from the improvement in performance. If you're a large company and it doesn't cost you much, if you get significant but not critical value from improved performance, if everybody did it, the amount of hardware you'd have to buy would go down noticeably. Now, it's not clear that people want to do this because there's a cost to just setting up the infrastructure, but this is a real serious economic model, and I think I believe it, because I've thought about it for a long time, and I can't seem to convince myself that there's anything wrong with it. Does anybody see anything wrong with it? At least, remember, I haven't made any statements about numbers or anything. This is just how to look at the problem. Does this seem reasonable? Does anybody have any thoughts? Okay, well, this is the most important part of the talk. Once we get past this thing here, this is what we're saving. We're saving all this money because we're not spending it. We're getting the same utility, but we're saving that much money, that rectangle of money. This is the incremental cost savings. Now I have to ask, what does this tangency point here mean? We have 2 points where the utility curve crosses some cost function. What does that mean? Does anybody know? Okay, it's a trick question. It means absolutely nothing. These are 2 superimposed curves with different units. So I could lie to you all and say it meant something, but I promise you it means nothing. Okay, good. What's important is that these things line up on the horizontal axis. So if you just think the vertical axis, you think of the horizontal regions lining up with the cabins. That's all you can get out of that. Okay. So that's pretty much the end of that. This was an introduction based on an airline analogy. Now I have to ask, which airline do you think I fly most often? Good. If someone said American because it's in italics, whenever the answer is part of the question, go with it. AA, Allocator-Aware. Okay? American Advantage, I have the credit card. Consider this an AA meeting. Okay, don't forget AA, very important. We use that a lot. This is the original diagram that was in the paper that I wrote, and it looked opaque to me when I first tried to present it to people, and they said, what? But now you understand. Okay, discussion? Okay, questions? Okay. All right, styles of allocators. Really, I'm going to jump through this because it's not important. All of the ways we achieve allocator-aware software are pretty much the same with the exception of C++11, which is so horrible we won't really talk about it. C++11, well, I guess we have to talk about it. PMR and C++17 are really kind of the same thing, but they're slightly two different styles. One of them I invented in 1997, and one of them was adopted in 2017. But they're basically the same thing. And then there's this thing that's going to come up on Wednesday that you definitely don't want to miss. And from these 3 models, there are, from these 3 models, we get these 4 styles. And so they all do, as I said, they all do the same thing basically. They give you the same kind of benefits, except for C++11, which is too painful to talk about. But basically they do the same thing. So it doesn't matter. You can just think of them all as allocator models. They're all allocator models. Okay. So C++11 is compile time centric. It has some advantages. It has the least overhead, but not by enough to care at all. So that's another discussion. The downside is so extreme that people don't use it. So if you've got a product that's absolutely awesome that nobody uses, maybe it's not that good. So C++11 is a non-starter, and we don't even consider it. Then we have the moderate cost style, which is the BD style. That's the BD development environment, sometimes basic development environment, sometimes Bloomberg development environment, but it's come to be its own thing, so BD development environment. This is runtime centric, and it's not so much that we need the runtime flexibility, it just gives us the interoperability that we need, and it turns out to be a very, very good model, very easy to use. We know we've been using it for 20 years. We're very happy with it. The cons are, and again, they're cons in quotes, it isn't literally zero overhead, but for all intents and purposes and measurement, it's zero overhead. That's my claim. There is, however, a significant implementation and maintenance cost if you do it by hand if you're a large company. So if I'm creating my own software infrastructure, yes, there's a cost. You have to actually write a standard map in a certain way. Now that we have C++17, we get the standard map for free. We don't have to worry about that. But before that, we had to do it, and it was expensive. So with PMR, which is really the same thing, and we do plan to migrate to that, it's the same style. It does it in a more C++-ish way, but basically it's the same thing, small syntactic differences. And as I said, we plan to move to that over time because why not? We want to be interoperable with the ecosystem, and I'm here to make sure that the ecosystem is interoperable with me. So we're trying to come together on some even ground. Hopefully you'll all change over to the polymorphic memory allocator right away, and it'll all be good. But I realize that's going to take time, and that's why we have put in a lot of effort to make it as easy as possible in the future so that someone would go, well, why not? Well, why on earth not? That's the goal. So language support for allocators in the PMR model, not in the C++11 model, will turn out to be the end of the rainbow for us. That's what we're working on. Some annotation will be needed, but I don't even want to go into this because this is all the Wednesday talk, the mid-afternoon talk from Pablo and Alistair, and I strongly encourage you to go see that. And I just make the analogy, you know, before we had virtual functions, we had arrays of pointers to functions that you had to create yourself in C. Who would do that now if you can just say virtual function? Imagine if it were easier than that to have a class become allocator. Just think about it. That would be great, but we will talk about that later. Okay, so they're all about the same performance. We're not really worried about that. I just wanted to let you know that there is a range and we're moving in the right direction from doesn't work to I'd rather kill myself than use it to I'd rather I drink battery acid than use it to I'm totally happy with it. That's the trajectory. Questions? Okay. So performance benefits. I have to ask, is there anybody out there that still believes that custom memory allocation adds no benefit to performance in any circumstance? I hope not. Okay, good. Let's skip that. So there are two kinds of ways that performance can benefit. One is we can make the cost of allocating and deallocating itself less. That's one way. The other way is to improve the locality of access even if there are no allocation and deallocation instructions going on for days. Okay? Which do you think is more important? The first or the second? There's a difference. It depends. Oh, it clearly depends. What I'm saying is, in order to measure the first one, we have to disable the second one. Because if the second one is enabled in any way, it dominates the first. So in order to measure the first one, as I said, we have to create benchmarks that hide the second one. That's how powerful it is. Okay. Short-running programs, faster allocations matter. So if you build the thing up, use it, and it goes away, allocation matters. But imagine if you build something up and then use it for days. How much does the allocation matter? What matters is, did you allocate the memory locally so that when you go to a region for a period of time, is all of that in main memory? Is it all in L3 cache, L2 cache, L1 cache? Do you see what I'm saying? That's what matters. Okay, so common usage pattern. Build up a data structure, a fewer no deletes, access them briefly, tear them down. We use a monotonic allocator for that. That works really well because it's a no-op to deallocate, but if you're not really deallocating anyway, just don't worry about it. Just build it up, use it, get rid of it. Another common usage pattern, we allocate and deallocate blocks of a few distinct sizes. And this isn't unusual for object-oriented or object-based programming like C++. And so it's very reasonable for us to use a multi-pool allocator. This is another usage pattern. It does improve performance. If you don't believe me, if you want to go view the C++17, CppCon 17 or Meeting C++17, you can see the 2-hour presentation where 4 benchmarks are described, and you'll have no doubt that allocators do what I'm telling you they do. I assure you. That was compelling. Usage pattern 3, we need to destroy many objects at once. So imagine that you have some sort of data structure and you've been using shared pointers and everything to keep careful track of things. Well, you know, it's entirely possible that you build something up, it's cyclic, it's whatever it is, and then you just say, goodbye, and it all goes away in one piece. And you don't have any of the problems that you would have had having to go chase down individual pointers and management, whatever, and it runs a whole lot faster. So we use that, what we call a managed allocator for that. And again, we're not really talking about the details here. I'm just trying to convince you that, yeah, we got the goods here. This one is not a question. Locality of data in time and space is also important. There are many levels of hardware caching, as I mentioned. Long-running programs that repeatedly allocate and deallocate can diffuse across memory that was initially local. This is a big deal. I can start a program, and then things move around. Move is a bad word in my life, because when something moves from here to here, I still have to access it over here while I'm working closely here. That access can be an order of magnitude slower, or worse, if it's paging, oh my. So when you get programs of substantial size and the data starts to diffuse, not fragment, diffuse around the memory, then you no longer can fit it all in one place because you have chunked memory, you have pages, you have cache lines. And when that happens, your program slows down very, very noticeably over time. So one of the things that allocators gives you is they retain, they're kind of like, keep the local pools of memory local over time. Okay. Loss in locality really does overwhelm anything you could possibly hope for in terms of allocate and deallocate performance. So just know that. So again, I said local allocators attenuate diffusion. They also, and I'm mentioning this for Alistair, they also help with fragmentation too, because fragmentation is not diffusion. Fragmentation is saying I have plenty of memory, but it's all in little pieces, so there's no space big enough for me to allocate a big array. Can't do that. Allocators help there too. All right. Local allocators facilitate threading. Of course, we know that we can have thread local storage, but we can do much better than that. If you put the allocator with the subsystem, then you can take advantage of thread pools. And the thread pool doesn't need to have affinity with the subsystem, because the allocator, all of the stuff that needs to be done is all encapsulated in one physical region. And so when the thread, who doesn't know anything, comes along, it just works on this part of the system. It doesn't bring with it, doesn't have to map its own thread local storage. You aren't locking a thread to a particular subsystem. So the highest performance, most flexible software you can write doesn't do thread local storage, it does local allocators. Okay. And by the way, you can write all of this by hand. What I'm saying is you can get all of it at premium economy prices, but you're getting almost first-class performance. Keep that in mind. We're selling something at an extreme discount. Achieving memory requires, good performance requires global knowledge, understanding of different allocator characteristics, and you just can't do that just sort of by magic. In order to use allocators well, you are not a junior programmer. You're also not necessarily, a rocket surgeon or somebody really at the extreme end. You're a sentient person who is interested in taking it to the next step in performance. You don't start with this, but when you see you're falling short of what your needs are, this is another tool in your toolbox. Discussion? Yes? Okay, the question is about J.D. Malik and other common allocators that have improved dramatically since the 1980s and 1990s, which were largely coalescing allocators. The answer is they do the very best they can do, but they're global allocators. What we're talking about is something where you have looked at your opponent's cards at poker. You see exactly what they are, and then you raise. What are you going to do? They don't see the cards. We see the cards. So we know exactly what's going on. So we cheat. And we win by ridiculous amounts. But they do the best they can. You'll see, that's one of the concerns. It's like, wait, we've been working on these allocators for years. They must be awesome. They're awesome if you don't see the cards. Okay, anything else? Questions? Okay, let's see what I can do now. Costs. Okay, so I told you that these things are expensive. They're awesome, but they're expensive. They improve performance, but we have to do some stuff. So there's two kinds of costs. There's the upfront cost of creating and maintaining the allocator-aware software infrastructure, and that is substantial. And Bloomberg has a very large organization that does software infrastructure for a much larger organization that does application development. A lot of people work on this infrastructure, and it's hard, and it's made harder by making those things allocator-aware. It's a lot like const. In fact, Matt Ostrom many years ago said, allocator awareness is like const on steroids. Once something is allocator aware and you don't propagate that up the chain, you've lost that ability. And so what has to happen is everything at the bottom layer, including the standard, which is why the standard has allocators now, and proper ones, it has to be allocator aware. At some point in the system, as an economic choice, you might say, I don't care about allocators. I don't really need to use C++ anymore. And then people start using JavaScript wrappers and whatever, and that's fine. So there's some point in the system where you stop worrying about performance. But when you're a hierarchically reusable infrastructure, you can't because some of your customers need it. Therefore, you must address the lowest common denominator, which is not a bad thing. It means that they need the lowest level support, which is actually very high level support, very granular support. So there's that cost, and then we're talking about plumbing, and we're talking about all kinds of things, mostly borne by the infrastructure developers. Then there are the incremental costs of exploiting or ignoring allocators. If you have an allocator-aware infrastructure, you might see extra arguments in the constructors. You might see more constructors than you would like to see. It's what happened with templates before we had variadic templates. The pain of variadic templates is writing them. Using them is pretty simple. You don't have to look at the code. You know what you're trying to do because you understand the variadic concept of the implementation. It's the same kind of thing. Allocators have a variadic notion when it comes to constructors, only constructors. But then after that, it's used the same way. And mostly the only inconvenience is in some cases you have to put the allocator first when you create it. Some cases you have to put it after. Most of the time it's after unless you have a variadic list. So it's not that big a deal for users. It's a much bigger deal for implementers. There is the ongoing burden. I mean, there is some cognitive cost. Wait, that's an allocator thing. That looks like fun. That will cost a company. Somebody who is naive going off and using an allocator without knowing how to use it could cause themselves trouble. So that's a real cost. But it's borne by most application developers, but it's tiny. All right. So converting an allocator unaware class to allocator aware. For typical classes, it's relatively straightforward. You add an optional trailing allocator to every constructor. Forward the new argument to the base classes and the data members and so on. Demote the type of not speaking right. Denote the type is AA by using an allocator trait. So this is just the mechanics of doing it. It's boilerplate. It's standard. It's not exciting for almost any type that you would run across. No big deal. But it is work, and there's more code. Non-typical classes can be more challenging. Many of them are already in the standard, so you don't have to write them, thank goodness. But occasionally people will need to write more complex ones. And as soon as you start to get to something that's a template, or some sort of thing that itself doesn't care about allocators, but something else does, now it gets a little more complex. We've got stood vector. And vector is interesting because now something happens when you add an element. It's not just a construction. Plumbing has to occur as elements are inserted and removed. That's interesting. So that's new. Then you have even more crazy things like pair. And pair is like really problematic. We have Pablo who can attest that pair is a bear. And then shared pointer is its own thing. You get a PhD in shared pointer. But we're not going there. That's not the point. 99% of what you do is straightforward. So the maintenance burden, people ask, well, how much of a burden is it? Some measurements suggest it might be around 10% code bloat, 10% more code to maintain. Is that a lot? Yeah. If somebody told you you're going to need to hire 10% more people than you used to because you have 10% more code, well, it's not really like that. It's really boilerplate code, and as we all know, if you have very regular code, it's not as complex as very intricate code. So if you have a systolic array, it's not really crazy. If you have custom logic, that takes up the same real estate on a chip, that's really hard. So they're not the same complexity, but still, you could make an argument that allocators are expensive in that way. These are 2017 measurements of BDE's infrastructure. There's more training, clearly. I mean, look at me, I'm out here training. So there's more training. There's an opportunity cost. I made Alistair go think about this. So instead, he's not working on something else that would add value to the firm, right? There's an opportunity cost here. It took him a ridiculously long time, and not his fault, to test the standard unordered map because of the way it's designed. And once you add allocators to it and all the interesting things, it's a challenge, not to be underestimated. Other important projects might be delayed. So we have this opportunity cost, and yet we still think it's important. So mitigating factors to the upfront cost. We can automate it. We have this tool called BD Verify that is available, and I'm going to start working on making it more generally updated and available now that there's going to be a lot of advertising of the kinds of things that are available in BDE, particularly because I talk about them a lot in the book. So when I want to go to an example, rather than having to show you copious amounts of code, I say, go look here, and you can actually run it, see what our stuff looks like. So that's a good thing. Our Bloomberg 2020 vision will eliminate most, if not all, of the plumbing, and the technology itself is a substantial cost. Bloomberg is investing a tremendous amount of money, serious, real dollars, to discover what it will take to alleviate this burden just for them. And then they're willing to share it with the world, which is really cool. So think about self-driving cars. I mean, if you had a self-driving car, you don't have to make it drive. You could drive it. But the cost of a self-driving car, once the technology is in place, is about the same as a regular car. All you need is a few more sensors. The software is certainly not the once it's there, it's there. So really, it's going to be quite a boon to everybody to have self-driving cars. And you might say, well, I don't know, I've made it this far without allocators. Do I really need them? And in the 70s, people didn't need cell phones. They got along just fine. And then what happened? And then somebody invented the iPhone, and then now we can't live without them. So once you have them, you might not want to give them up. And we have people who have experienced this and would fight to their, mortally if somebody tried to take away their allocator. Okay, typical cost of using an allocator-aware software infrastructure is small, and we'll discuss style in a moment. It's much easier and faster than rolling your own. You just supply an allocator pretty much and you're done. It requires additional testing effort, but if you don't need custom allocation, you just ignore it. You test the same way you used to, and it's opt-in. So anybody who doesn't want to play doesn't have to play. If you followed anything about what went on with modules, one of the strong requirements was you can adopt them at your own speed. You don't have to adopt them in lockstep. That was a huge requirement, it was a business requirement. The same would have to apply for allocators. You'd have to be able to ease them into your system as needed, anywhere in the system, and they would have to continue to work with existing code. So I want you to know that we're not insane. We actually have to run a business, and so that will happen. There's an additional cognitive burden. Users will still see AA features, right? Enlarged programming interfaces, trailing allocator arguments, a little bit more boilerplate English contracts, optionally specified the basic allocator used to supplies, that kind of thing. Also, the net benefit for those who exploit AA, while it's clear, the overall benefit for people who don't yet exploit AA is less clear, and that's really where the concern comes from. Because if you're already using an allocator-aware infrastructure, you wouldn't give it up. But for the people that aren't using it yet, it's like, do I really have to deal with this? Because I don't care. All right, then there are these kinds of reasonable concerns, like what happens if you have an allocator that you supply to an object and the object outlives the allocator that's supplying the memory? That's rare. People don't do that because they're smart people. They know about dangling pointers. And it turns out that in the C++ object model, when you create an object A and then you create an object B in the same scope, if B is the container, how could it possibly outlive A, the allocator? It can't. The only way you could do it would be to return an object that was poorly designed that held on to its allocator from copied by value. Don't even, I mean, it's a dangling pointer. Don't do that. Much more likely, much more frequent is that you'll use a special purpose allocator that is known to cause damage when misused in an inappropriate way. And that will require training. Most common one is to use a monotonic allocator in a loop, because monotonic allocators don't give back their memory. And if you allocate a million things a million times, eventually you will run out of memory and die. So it could be catastrophic, which is fine because you'll fix it, or it could be completely useless, which means all the work that you did is just creating a maintenance burden for the next guy when you leave. In any event, it's a cost. So we have incompatibility with some important features. Allocators just don't play well with them. And so as a result, these modern features are just sort of, we got allocators, we can write in C++03, we can do some nice stuff in C++11, but some of these Lambda things, and we just don't have a place to put them. They're not well integrated. So even though allocators are really useful for people who really have day jobs and do real useful work, if you're into C++17 and 20 and you're trying to use the latest and greatest feature, there's a chance you won't be able to also use allocators with that, and that's unfortunate. So allocators, for example, require a non-trivial constructor, so anything that the compiler generates won't help you. You have to do that yourself. Move variants are even worse. We have more things that aren't handled with allocators. Aggregate initialization is another example. But by the way, these things are fixed. If you have a different kind of solution, go see Alistair and Pablo on Wednesday. They don't interact with move semantics, though. The idea that our allocators don't work well with the modern C++ style of programming, that's false. And that's something that's been a pervasive myth. And for many reasons, and we'll talk about that after the sort of the partition that I'm going to get to, for many reasons, that's just bunk. So we'll talk about that later. All right, so lifetime management issues. The productive lifetime of an object must not exceed its allocator. This is important. Requires additional care by application developers, true. Limits applicability of certain standard facilities, yep. Shared pointer and weak pointer have some issues. But here's some other stuff. It's going to take more money from the company to deal with education tools and governance, additional administrative costs, proper training, code reviews. Developer-facing static analysis tools have been a problem, company-wide policies. This is not atypical of anything that's new and powerful, right? If you've got a powerful tool, you have to do something with it. People who are doctors are very useful. They have to go to school for a long time to become very useful. Then they're doctors, and then they help people. So multi-threading testing in and of themselves, really hard stuff. Not everybody wants to do that, but once you're really good at it, once you've learned it, it's very helpful. So the bottom line is there are real substantial costs, upfront library development costs, modest incremental application developer costs. Incredible value proposition still remains. We get great performance, but wait, there's more than that. If we don't have that, we'll have to roll it roll it ourselves. If we do that, that's very expensive, and those people that can't afford to do that will have to do without. So either we get this great thing at some considerable expense, or we get this, a few people will benefit at tremendous expense, and everybody else will go without. And that just seems very non-friendly. Discussion? Questions? All right, well, let me just try to be on time. That'll be fine. There's one question people ask, what percent of the code, what is the percentage of code that benefits from allocators? We don't know. But we know enough of it does now that it's useful. We suspect that the more people realize that allocators are approachable, the more code will benefit, the more people will hear, the better performance will be, and so on and so forth. But we want to accelerate that process by taking away all of the pain of experiencing the wonders and joys of allocators. So that's the next thing. So the next point is collateral benefits. We talked about performance, but there are a bunch of things that we get from Allocator-Aware software that we don't get even from first class. It's really important. Rapid prototyping is one of them. Imagine that somebody says to you, we've got this problem with this system. I'll bet you it's a memory problem. Go fix it. One way is to go and write your own custom data structure, plug it in, and see if it works. That's not easy. If you get it right, great. It's going to take a while to get it there and test it and whatever. And customers are suffering. Or you could take Allocator-Aware software infrastructure, glue a couple of things together, or even just drop something in, try that, and that might fix the problem in an hour. And if it does, you're a hero. And even if it doesn't completely fix it, it will attenuate it while you go off and know you're doing something useful. On the other hand, you could go off and do something for a month, plug it in, and it doesn't help. Now where are you? Do you leave it in there so you don't embarrass yourself? Or do you take it and say, you know, I blew it, I lost a month. What do you do? So that benefit does not come from full custom design. That benefit comes from the rapid prototyping of pluggable, chainable allocators. That's really important. I would think that alone would be convincing. Anyway, it's unlikely that these custom allocators, a custom data structure is going to provide the collateral benefits we're talking about. So what I'd like to do is briefly go through the collateral benefits. So designing with AA is low cost, low risk. We talked about this. You just plug it in, you measure it, you tune it, you repeat as needed, you deploy immediately. That's awesome. That alone, you know. You can use it as a proof of concept to justify a real project. There are some data structures that must be written. But if you say, I can achieve 60% of what we need in 1 hour, give me a month and I can get the other 40%, people will be very happy. Okay. So BD-style allocators are chainable. What does that mean? Means that we can take an allocator that does one specific function and have it draw from an allocator that does some other specific function. So we can chain them together. A small block allocator could fall back on a large block allocator. So you have the rapid back and forth over here, but when you need a massively large amount of memory, instead of getting it from all different parts of the system, you get one big lump that's contiguous and not fragmented, and then you bring it over in one piece, which is very quick, and then you apply the pooling to that. And it all happens because it's all composable. And so this is just a wonderful thing that you get for free. Some features like metrics, I can put in a test allocator, I can put in a counting allocator. There's all kinds of stuff I can do to just insert into the chain and get information. Measurement is an enormous benefit that we get from this, object-based measurement. You can measure the memory in a subsystem of many subsystems all using the same types. And it scales infinitely. These are really important things. There's no question of scale. The test allocator is something Attila from Bloomberg is going to talk about the test allocator. I'm not thinking it's Thursday, but in any event, if you're interested in that, you can go see that. Log, allocate, and deallocate calls, match deallocations and allocations. You can test exception stuff. By throwing a bad alloc, you can do memory range overflows with sentinels. It's non-invasive, huge. It's non-invasive. You can link it into the largest thing you want. There's this wonderful example. I have something in volume 2 of my book that says, use dynamic cast only when you don't need it. That's literally the name of the chapter. And it's really important, or the section, I should say, not chapter. And it's really important because what this thing does is it uses the allocator, the ubiquitous allocator protocol, abstract interface, or in the case of C++17, the allocator vocabulary type, as a Trojan horse. And the thing that implements this thing, the memory resource, is both an allocator and a monitor. And so the thing that's receiving what appears to be an allocator asks, hey, allocator, are you a monitor? And if the answer is yes, it can deliver its own information invisibly through this allocator, this ubiquitous allocator interface. So what we've provided is a vocabulary type that can serve as a Trojan horse that can allow people to opt into object-based monitoring. It's amazing. It's a wonderful thing that you can do. It's all made available because we have ubiquitous uniform allocator interfaces. So it's a wonderful thing. And none of this goes away when we make it better. Everything gets better when we make it better. We don't give up anything. All right. When I first joined Bloomberg, before that I had used allocators to make people in the financial industry successful in deleting their financial models. When I got to Bloomberg, it turned out that they needed to place whole objects in memory-mapped memory, or IO-mapped memory, and you couldn't do that with the standard library, and we were forced to fork the standard library to introduce allocators so that we could save a vector of whatever in this range, because new and delete obviously aren't, placement new and delete will place the footprint, but they won't place the entire object. So out of the box, this stuff worked in a completely different arena, and what can I say? It was an immediate success in a completely different area. One of the things C++ is all about is if you add a new feature, it should be useful in many different ways, not just one, not just performance, although that's a good reason. But this is useful in so many different ways that I just wanted to mention placement as being one of them. And I'm putting this stuff on the screen so you can read it, but we call that thing that allocates memory from this special place, we call it gmalloc. But really what it is it's attached to an allocator, and you use it just the same way. Everything you do, you just build it with a gmalloc allocator, and it just works. Literally, it just works. It's one of those amazing things. And I think I mentioned garbage collection and traditional pointers. This is an architectural thing. This is not just an optimization. You actually can design your system differently. You can design it cleaner and simpler and not have to worry about cycles and other things. So this is really an architectural benefit of having the notion of something that can just say, all of you go away, I don't care. And that works very nicely. So it's an open-ended thing. It's a pluggable system. We don't really care that we have the runtime. We can assign the thing at runtime. That's not really the most important thing. What's important is the interoperability we get from being able to hold on to an allocator. We don't have to make everything. Okay, we don't have to make everything a template in order to use it. This is one of the big problems with the C++11 model, is that in order for something to consume something that's allocator-aware, it too must be a template, and so it doesn't scale. So that whole idea was just a necessary evil in getting to where we are right now. We knew that when we first proposed it in 2004. It took people a while to realize it. I understand that. Who would ever think that having a virtual function could ever be a good thing when it comes to memory allocation? And yet, how is shared pointer implemented? With type erasure. And how does that happen? Using good old-fashioned object-oriented programming. So, just because you're old doesn't necessarily mean you're bad. All right, discussion? Okay, questions? So we're up to that point. I said I was going to try to get done by the end of the hour. I'm 13 minutes ahead of schedule. Any questions about this? Because I'm just going to charge ahead. Unless you, there's one.
So maybe in the cost section, how does this interact with other sanitizers and tools like Valgrind?
You're asking how does this interact with sanitizers and Valgrind? What this are you talking about? Okay, so in this talk, we're talking about library-based allocator-aware software. So it's no different than any other software. It's just plain old software. So it interacts wonderfully. You see what I'm saying? There's no difference. If something takes a pointer, it takes a pointer. No difference.
The point is, if I leak an object, it's allocated with now can be for delete. The sanitizer will point me to that area. But if I leak an object, it's allocated with.
Oh, okay. So the question is, okay. So this is interesting. This is good. Let me try to rephrase this. If you pool memory, no matter how you pool it, whether it's an allocator or a pool or whatever, and you fail to return memory to the pool, and then the pool itself returns everything, are you leaking memory or not? It's kind of funny, right? You're not leaking memory because the thing doesn't actually show up as a leak. But you meant to give it back, and then it gave it back for you. And that's a subtle, that's not what you intended. It is what it is. But we have ways of detecting that because when we test our code, we put in a test allocator, and the test allocator mercilessly accounts for every bit of your, so you don't worry about that. But very good point. So that can happen. Whenever you pool anything for any reason, that can happen. Any other questions? Yeah. Yes. So I'll just say that the question was, is this open source? If you go to Bloomberg's BDE, the GitHub, what is it? I wish I could remember. I should have it up here. Okay. So anyways, so just go to, it's GitHub, Bloomberg BDE. I think if you Google it, it'll show up immediately. Otherwise, buy my book because it's in there 1,000 times. And you can just go there and use this stuff right out of the box today. It's been there forever. I literally invented this 20 years ago. Not kidding. 22 years ago. Okay. All right. So classical allocators have been really bad. I said this in Lakos 96 that this class-based allocation is useless, and there are weasel words in C++ 03 that make allocators pretty much useless, and in C++ 11 they're a pain in the you-know-what. And in C++ 17 they're much better. So they're still not perfect. They don't interact with all the new language features, but they definitely add a tremendous amount of value at some cost. And then you've heard all the truth, and now people invent reasons. I say, invent reasons or reasons in quotes, because it's not that what they're thinking is dumb. It just turns out not to be founded in any reality. That's the only problem. It's just not true. So we want to talk about that. So one thing that isn't stupid, somebody could ask the question, well, we got state-of-the-art allocators, and someone did. Aren't they good enough or better? And as I said, the answer is they're as good as they can be, but they can't possibly compete with what we know. Then we have the zero overhead principle, which is like, do polymorphic allocators use any more space ever than the other kind of allocators, the C++ 11? And the answer is, yeah, they do. And it's a poor runtime performance trade-off. Now that's a laugh, because if you look at what you give up when you have an allocator-aware infrastructure, you're giving up something where no one cares, and you're getting it where they care dearly. So that's one of those. Then it's unmanageable to test and verify. That's a more reasonable argument. And then again, I would say, well, if you can't handle it, don't do it. It's incompatible with the modern C++ style. This is the one I get militant about. It's not incompatible with the modern C++ style at all. That is pure fiction, and that is an invented statement. Doesn't play with move semantics. Again, no, that's an invented statement. Move semantics doesn't play well with reality, and we know this. And anytime somebody is all excited about move, they need to learn what's really happening there. And yes, move is another nice tool in the toolbox to be used only when you know what you're doing. And if you don't know what you're doing and you start moving things all around the world, what will happen? Your diffusion will kill you. So you have to be very careful about that. And we have measurements, and we will publish them. And trust me, we will debunk this myth that move is somehow God's gift to everything, and it will kill allocators, because that's just not true. And then finally, which is an interesting statement, object pools and object factories, we've got those. Why do we need allocators? So in the very little time that I have remaining, I'm going to go through each of these, and then I'm going to plug out Alistair's talk and Pablo's talk one more time, and I'll be done. State-of-the-art global allocators. Have I convinced you? If I just leave this up, do I have to read this, or can you just read it yourself? This is a common concern. And it just turns out that there is no way to take advantage of all the good things that you get, all the collateral benefits, all the performance, with anything that you plug in one point. That's not how it works. So global allocators are not and cannot be sufficient. They're general purpose, for one thing. They have to work in all circumstances, for every program, not just yours. They cannot achieve the locality that we're talking about. They don't provide the collateral benefits. They don't provide the instrumentation, the placement, the rapid prototype. None of that. Next one, zero overhead principle. For all but the C++ 11 model, there's a little bit of overhead. What is that overhead? Somewhere in the object, somewhere, if we have an allocator, we're going to have to know what that allocator is. There are a bazillion tricks we can play to make that amortized to zero-ish. One of them, for example, is if you don't allocate any memory in a vector, you don't have to, you can store the allocator pointer in place of one of the other pointers, one of the other iterator pointers. So your footprint doesn't grow. In fact, a footprint in a vector can be 1 word, 2 words, 3 words, or 20 words if you want to do short vector optimization things. The size of the footprint is completely up to you, however you want to implement it. We have experimented. We know what the right size for a string is. We know that using all of the footprint for the short string optimization is not the fastest in our usage models where we've checked it. So we know. It's not a question of we do the right thing. We do what makes sense from a business perspective. So the zero overhead principle is, in spirit, fully lived up to because the benefits you get when you need allocators are so much higher than the almost unmeasurable costs of anything that could possibly be discussed as for, oh, I have this extra pointer in this thing. If that were really true and every single bit mattered, how could anybody justify having an 8-word string when the normal strings are 2 or 3 or 4 words? Why would you ever do that? The answer is you're trading off space for speed. People do it all the time. And in this case, it's a really huge win. Okay. So I just talked that through. I'll put these slides up. Neither the letter or the spirit is violated. And one thing that people have really cried about is virtual function dispatch. And it turns out that the only time that virtual function dispatch could ever matter would be in one of those programs where you're using a monotonic allocator. You create the allocator, and then you create the object that you're going to use it on right afterwards. Well, typically the allocator will have an inline virtual function, yes, and then the thing that you're creating is a template, and both of those are visible in the client's compiler, and the same code is often generated. We knew this was true in GCC a long time ago, and I'm sure Clang is catching up. But the point is, now that it's part of the standard, in that pattern, that's the only pattern that matters, the virtual function can be devirtualized to a large extent. So having said that, there's nothing to worry about. There's nothing here. Move along. There's nothing going on. And you can just do the benchmark, or just look at the object code, and you'll see. So this is not a problem. We make design trade-offs all the time. And these are different kinds of design trade-offs that can be made. And some of them are reasonable, but the trade-offs that we've made in particular for allocators, benefits of some with negligible cost to others, some benefits for a few but small costs to others, that's the kind of trade-offs we've made. What we haven't done is disenfranchised anyone. We haven't said, see that group, you guys, sorry, you can't program anymore. The rest of you, you're all good. We didn't do that. What we really said is, guys, you just won the lottery, and you guys, I'm sorry you didn't win the lottery, but you might have lost a penny. Sorry. But the point is the people who are over there doing that are doing that super high performance, low latency stuff where they absolutely have to have it. They're game people, they're finance people, they're people that are out there writing code instead of allowing another language to get between us and the hardware. So what we're doing is a huge service to C++ because we're staying down at the metal and we're not letting anybody else creep in. And that should be something everybody understands. We need to do that. That's one of C++'s charters, is to make sure no one can get underneath us between us and the hardware, not even C. Okay. So this is what we do. So some of us have decided to call it the allocator tax. Everyone must buy auto insurance. Accidents are unusual, but not rare. So yes, you might be one of the unlucky ones that needs insurance or allocators, but everybody pays a tiny tax, very tiny, so that you are whole when you need it. But it's really one of those extreme cases where everybody pays a penny and a substantial fraction of people get like $10,000. It's not a zero-sum game at all. And in those cases where you're getting the benefit, it's inside a loop, and it's really much, much, much more amplified than that. All right. Verification and testing complexity. Yes, it's harder to test. If you don't use it, it's not more. But if you do use it, it is more, granted, and you have to learn how to do that. You can opt in. Anyway, Winking out. This is something we didn't talk about a lot, but the winking out part is you create a whole system and then you just pull the plug and it's gone. No destructors are called. Nothing is deallocated individually, just gone. And this is legal C++, trust me. I have someone who can attest to it in the back. And it's fine. We can do this and we get the benefits of it. And if you're squeamish about it, if it makes you feel ill to do that, don't do it. But if it doesn't make you feel ill, then you can do it. And you can use the test allocator, go see Attila's talk, and it'll make you feel better. And also, if you go see Alistair's and Pablo's talk, that'll make you feel a lot better. So C++ encourages a style of programming where objects are moved and passed around by value. And somehow I should care, because it turns out that this style of programming is bad in general for infrastructure. Now, I'm not saying that if you want to write in a functional style that you shouldn't be allowed to do that. Not at all. But there are people that need to write in the most efficient ways, and those people need to be able to control their allocators and do whatever they're going to do. But even if we weren't talking about allocators at all, not at all, the idea of returning an object by value eliminates pooling. Do you see why? If I have something that returns an allocating object by value, even if I don't have any control over the allocator, I must construct that object when I call that function. And when that's done, it will be destroyed. And every time I call that function, a new object will be constructed. Whereas, if I pass that object in once, having constructed it, I have control over the allocator. It's constructed once, it's used many times, it's destroyed. And that's what pooling is all about. And the C++11 style prohibits that. So just know that people who are advocating that need to think again. It's inherently inefficient. It has nothing to do with allocators. Just said all this. Returning the object by argument is faster. And it doesn't matter that it's not about move, by the way. It's about return value optimization that gives us essentially the same performance for one call versus one pass-in. Those are pretty much a wash, pretty much. But if you were to call the function twice, then there would be no question. So, but we want to design our code in the way that gives everybody the most fine-grained control possible. And so anyway, I'm just putting these words up for people at home to read and for you to read. But the idea is we are not doing something that prohibits anybody from doing what they need to do. They can go ahead and do it, but they can build that on top of our stuff. We can't build our stuff on top of theirs because ours is more general. Theirs is less general. Okay, move versus allocate. So there is a myth that moves are always better, but we know that's not true. We know that moves are good in certain very specific situations. They're good when you're working in the same memory pool. So, for example, if I have a vector and I want to do an insert, that's fine because the vector is all going to come from the same allocator. So while I will lose a little bit of benefit, I won't lose locality. I won't miss out on what we'll call constructive interference, which is having two things that get on the same cache line because they are part of the same working set. That's a good thing. What we will lose out a little bit on is prefetching and some stuff having to deal with n-way caches and how memory banks are accessed. So moving does muck with us a little bit, but it's okay. But what we can't do is we can't lose the locality. So as soon as you try to say, I want to move this, but it's in a different memory pool, so I can't use allocators, that is the tail wagging the dog. As soon as you find out that you're trying to move across a memory pool, you'd better start thinking about how you can re-architect your system so you don't do that. Okay. Compared to other A alternatives, like factories or object pools. Think about it. Factories and object pools are things at a higher level of abstraction that need memory. Where do they get it from? They need to get it from allocators. And so all of these things, these object pools and whatever, that traffic in constructed objects had to create the objects in the first place, and you want to be able to source that memory from somewhere. So the traffic cop is the allocator, and the abstraction is still important for application developers, but it's not one or the other. And because we have a hierarchically reusable system, if I have allocators all set and done, and then I have a whole bunch of stuff that I use to build object pools, and then I have object pools, and then later I need some other object pools, I go over here and build my other object pools, and instead of writing them from scratch, I use the very next layer underneath that I use to build these object pools, and that's called hierarchical reuse. And that is what my book is about. That's what I've been working on forever. And this all fits together into that seamlessly. Objects are not a replacement for allocators. Object pools are not faster than allocators. They're a different level of abstraction. And since I'm pretty much out of time, I'm just going to put this up. Anyway, if we do build our object pools out of allocators, we get the collateral benefits. If we don't get the collateral benefits. So why wouldn't we build our object pools hierarchically out of allocators and allow all of the benefits to flow seamlessly in the system? Discussion. All right, well, so that was the outline. I'm going to close this up and say custom memory allocator strategies impact performance, instrumentation, object placement. Historically, we had to write our own. Allocator-Aware software infrastructure has real costs, the fixed engineering cost to create the darn thing, and then there's some added operational costs. There's a big resistance because of C++11, but investing in AASI, Allocator-Aware software infrastructure, is an economic decision, and it provides nearly the same runtime performance, lower incremental costs for users, does require a substantial upfront cost, comes with important collateral benefits. The C++11 experience created all kinds of FUD which we need to overcome. And the question is, do the benefits outweigh the cost? That's really the point of this whole talk. Do they outweigh the benefits outweigh the cost? How do you feel? You all have your own opinion. Yes, no, wait. But if you look at this picture where alpha is, I don't know where you are on this curve, but wait, what if we had some magic dust? Well, we could take away all of the costs and all of the imperfections of allocators so that the only thing that we had was goodness. Then what would you say? So, should we be investing in that magic? How can we afford not to? Because we think it's worth it now, but we know that when we perfect this technology, there will be no discussion. And we'll change the ecosystem, and the default will be allocator-aware containers. We know this. We're just waiting for other people to find out. So what about this BB20V, Bloomberg 2020 vision, is something that I sort of thought about a couple of years ago, and now people are starting to go, oh yeah, 2020 vision, isn't that cool? But yeah, this is what we're working on, and it pretty much eliminates all the costs. It's analogous to self-driving cars. It reduces client costs to bare minimum, gives them everything they want, and it's really the same. They really are very much the same as virtual functions are today. That's the picture. We started out here. I want to thank Pablo for these temporary slides that I'm going to have to help him and give him better slides. We started out here. We got C++11. We got 17 and 20, and now we're working on it. And that's it. Thank you very much. Question in the back.
So the one penny cost is
Thank you. This is good stuff. So the one penny cost is whether somebody in my organization uses Allocator-Aware and that sort of diffuses through the code base, or is it if I set my software and I really don't care about Allocator-Aware, is any of the BB20 vision or the impact from that going to add extra cost to standard C++ or standard C++ library?
So the question again is does allocator awareness satisfy the spirit and the letter of zero overhead principle? I'm going to argue that it does satisfy the spirit, and we can debate whether it satisfies the letter, but even virtual functions don't satisfy the letter, because once you have a virtual function, you have a pointer in your right.
Sure. So, but assuming that I write code without virtual functions, I don't get to pay for that, right? So
right. And if you write something that isn't allocator aware, you don't pay for that either.
Okay. Thank you. That was
right. But who would? Because I'm telling you, there's no. You will never be happy with yourself.
Sure, no, I don't disagree. I just wanted to
Okay,
realize. Okay,
sure.
cool. Thank you.
Okay. Any other questions?
Regarding pass by value or value semantics, I heard a speech by Chandler Cruz from Clang from LLVM, who strongly disagree.
We
with
tend to disagree on occasion.
Yeah. But couldn't there be some sort of middle ground? Perhaps it's not necessary to pass in the object by reference to a function. That's actually a return value. You could, if it's kind of a factory function that produces an object, you could just pass a reference to the allocator and it could return the object by value.
Okay,
That's one case. And
that question's very helpful because it illustrates the point that I said. Even if you pass in an allocator, that gives you control over how the object is placed, but you still have to construct it each time. So if you have to construct it each time, you can't pool it. And if you can't pool it, you're losing out on the opportunity to do object pooling, which is really important.
Okay.
I don't think everybody has thought everything through at the same level of detail for every single thing. Chandler is an awesome person. He's also an expert ballroom dancing instructor.
But he knows what difficulties it creates for the compiler regarding alias analysis. That's what I'm saying. Maybe it would, in some cases, outweigh.
We need benchmarks to have that alias analysis thing, but I'm pretty sure I'm going to win.
Okay.
Pretty sure.
Okay, I'm a wrestling match. Okay.
Yeah. Oh, Pablo wanted me to point out, if I call the function once, I won't win. If I call it just once. But if I call it 2 times or 3 times or 4 times or in a loop, I win. We know this. Okay. Any other questions? Yes. Microphone.
It's right here. You have a lot of data collected at Bloomberg for a lot of this allocator stuff.
It's published.
What was that?
You can go to the standards committee. I have data coming out my yin-yang.
Absolutely.
always.
So my question is, do you have any insight on specifically more embedded applications and
We don't
whether
do- well,
allocators
we don't-
apply there?
Except for this one little thing that we have called a B unit, I don't think we do embedded applications. So I don't know. I don't have data on that. However, if anybody were interested, send me mail. If you do embedded applications and you want to try to work with me, allocators are not the same kind of unbounded thing that they are when they're a global allocator. So if you're an embedded system and you want a nicer way to do something that's deterministic, allocators can be your friend there because they don't go off into la-la land necessarily. You can have something that has a tight time bound on it.
Absolutely. Thank you.
Sure. Anything else? All right, well, thank you very much for coming and staying a little late. I really appreciate it.